Hi, this is a lecture supplement for week 6 on the section DOE Examples and Structure up to Characterizing Designs, and to the end of that we will cover optimizing designs in this particular lecture. I just want to be very quick about this, and I don't think this needs to take a very long time. Mainly what we want to discuss in this is just a very quick review of what DOE, the basics are, and then take you through essentially a paradigm that a lot of people have if you're embarking on sort of an area of experimentation. And so, for example, you may be starting to work out in a call center. You may have lots of ideas. The first step would be to essentially say, we'll get lots of ideas, just like you would in a Six Sigma project, right? If you're trying to improve the handle time or the first call resolution or something like that, you start out with getting lots and lots and lots of ideas, and these would be sort of the a general large number of arrows over here. Now suppose, I think like a lot of places, you may have found like 30 or 20 or whatever arrows of all the different things that could be affecting, say, the AHT. Lots of things. Let's suppose that that's what happened. How would you systematically tackle that? Well, the paradigm in here gives a DOE structure to tackle that. And the idea is that first you would do what's called a screen. And that would be take a relatively small experiment to just separate out if we had factors A through AZ, right? So A, B, C, all the way to, maybe not to AA, maybe to AB or something like this, all the way to Z, and then AA, AB. So that would be 30, I guess that'd be 28 factors, But we could obviously have any number to screen and see which ones are really the heavy hitters, to get maybe, it turns out that maybe A is heavy hitter and F is big and H is big and so forth. That would be the first thing. The second thing would be to say, okay, how can you then take that and run a characterizing design? Now, the designs that we did the first time around were basically characterization designs, Res 4, Res 5 designs. To put this into context, these are generally Res 3 designs, and these are generally Res 4 or 5. Okay, so characterization designs. And then the third one is to optimize. As I said, we aren't going to cover that in this particular lecture, but that is to say, let's take a couple, maybe one or two, not 5 or 6, but really 1 or 2 of these heavy hitters, and let's really find the absolute sweet spot for those heavy hitters. That's what optimization is really about. And for those, we often do full or even special designs. So I want to just cover very basically what's going on in these, but you can think of them as simply Res 3 or Res 4 or 5 designs. Res 3 for screening designs, Res 4 or 5 for characterization designs. Now, here's the nice or the happy coincidence, is that if you're thinking ahead, a lot of times when you run a Res 3 design, it ends up effectively being a Res 4 or Res 5 design, because many of the factors will turn out to not be significant, and you can actually use that data to characterize the response surface or the full factors pretty well anyway. Okay, so let's just kind of get to that, do the example. We'll do a couple of examples. So we'll go through again the basics of DOE and the framework for approaching. And then we'll do an example of screening and seeing how that can flow into characterizing designs. Okay. Now, one of the views of Six Sigma or Lean Six Sigma is that what we're trying to do is we're trying to really essentially find all the X's that drive that Y, right? So the epitome or the peak of that is DOE, where we actually jiggle the inputs to figure out that exact function, or pretty darn close to it, so that we can understand which factors, which noise factors, all of that, add in and we get. All right, now just to keep in mind that DOE, whenever we're going to be running a DOE, now this does not apply to, say, doing DOE with a in the data collection piece, right? So to say, well, I'm going to use thinking about DOE to help me understand what sample size do I really need to be able to effectively get the right amount of data or anything like that. What I'm talking about is actually running a DOE. And if we're talking about that, it should be preceded by earlier tools. So Fishbone, FMEA, process mapping, graphical, or looking at existing data historically. We shouldn't just go straight to brainstorming the X's, but really should have them from previous analyses. That's pictorially represented by this. DOE is really active data collection. That's really what it is. Now, one of the ways to think of this is it's a series of experiments. If you run one, that's a series of one. But to figure out or crack the code on this, right? And remember that what we had in DOE was we have a constant. That's that guy. And then usually we call this A, B, and C, right? The main effects instead of X1, X2, X3. And then here would be the interactions, AB, AC, BC, and then ABC. So this happens to be a three-factor model. So it has, let's see, let me count the coefficients. 1, 2, 3, 4, 5, 6, 7, 8. So we would need to have 8 runs to do a full factorial. Notice that we have 7 different things that are available to be estimated plus a constant. Okay? A screening design for 8 runs would essentially be something where you could fit up to 1, 2, 3, 4, 5, 6, 7 factors. So A, B, C, D, E, F, and G, and you would only run 8 runs. Now, the big assumption there is that you have no interactions, and so you can screen out the big factors from the small factors. That's what's going to be a screening design. Anyway, we're just doing backups here, or a quick review. Okay, keeping on the terminology, what we're trying to do is we're trying to find which X which most affect a Y, and our response is that Y is our response. Her terminology is that Y is the response, X's are the factors, A, B, C, D, and E, and so forth, and that we have control factors. Those are the X's that we can do something about, we can adjust them, and we have noise factors, X's that we can't really control. We have levels for each of those factors, which are the settings, usually a high and a low setting that we set something at. And then we also have something we didn't talk about, repeats and replicates. Repeats are things where we run the same experimental setting multiple times. And replicates would be where we run additional randomized runs with the same setting at different times, maybe sent to a different area or whatever. Okay, those are very close to each other and not enough of a distinction to really spend a lot of time with. Choosing the levels, again, we want to choose basically near extremes but not extreme extremes. So for example, given on the upper left-hand picture, that's what you would want to do for, say, a high and a low temperature of something. Not off the scale, but on the scale. You wouldn't want to pick them really close to each other, nor would you want to pick them so far extreme that it doesn't really represent reality. 3 strategies to help keep control the noise. One is keep constant. If that's possible, you can do it. Many operations it's not possible, so you are stuck with thinking about making blocks and nuisance factors. So sometimes you can include the nuisance factors right in there. So in the call center example that we'll do, experience level may not be something that you can control for. It's something that exists, right? If you take a person, that person may have a lot of experience or a little experience. You can certainly train them. That would be a proactive thing. But the fact that they have more experience or not would simply be adding into the noise. So sometimes even if somebody were using a poor tool, if they were really good at using it or if they were really experienced, they may actually get good results. Okay. So the framework that we're going to suggest in the case where you're doing this, where you come into, say, a call center and you've got lots of different variables, is to first start out with a screening design. Now, in many of your applications, you can go straight to characterizing designs and it'll work just fine. I think you'll see why. Okay. Now, the basic thing is that screening designs are used to eliminate the X's that have no effect on Y. Okay, they're very efficient at eliminating these non-important factors. Simple to set up, analyze, and provide a great basis for the more complex designs that follow. Second thing is designs for characterizing Y. That's what we've already done. we've sort of identified 5 or 6 critical X's, and then we run a moderate-sized experiment, like 16 runs, to be able to characterize them completely. All right, and then finally, designs for optimizing. Again, like I said, we'll do an extra session on that and record that separately. Okay. Now, let's do an example here. Suppose that we had a 2 to the k design framework, and suppose we have k factors, whatever those are. Suppose each of those factors can be set at 2 levels, then a full experiment can be done in 2 to k runs. For example, if my response is monthly sales, and my factors are A, B, C, and D, language, script, features, day of the week, and experience, we would need 32 runs, and the framework would look something like this. Now, going with what we had before, we'll note that because we have 32 runs, we have 32 degrees of freedom to be able to estimate our coefficients, right? Our coefficients of A, B, C, D, AB, AC, AD, AD. Okay, you with me? ABC, I'm sorry, BC, BD, and CD, ABC, ABD, ACD, and so forth, right? All of those things. So one of the things that we could do is if we had lots of other things that were in there, not just A, B, C, D, E, we could run many. In fact, we could run in 32 runs, we could handle up to 31 factors if we're doing the screening design. All right. So, and again, if we had if we decide to do 16 runs, we could look at 15 factors and examine them all in that run of the experiment. Now, what we're going to be able to do when we analyze this is that in a screening design, we're going to be using sparsive effects mainly. And in a screening design, often you don't have anything but the ability to look at these guys, in theory. Okay, you don't have any resolution to see these guys, or these guys, or these guys. What effectively usually happens is that when you have 15 factors or something, you start to cancel out these, and guess what? Then you actually do have a design where you can start to look at some of the interactions. Often happens. Here's an example of what a resolution 3 design looks like when you look at the aliasing. There it is right there, my ones with other 2-factor interactions. 1 plus 2 is equal to 3. 1 plus 2 is equal to 3. So that's sort of the main characteristic, is that they're resolution 3 designs. And we already talked about resolution 3, resolution 4, resolution 5. Generally speaking, when we're doing screening, that's this guy right here, and then these are going to be characterizing. Characterizing. Now, just as a rule of thumb, I've worked with a lot of engineers when I worked in a plant. It would be easy for us to get 30 or so factors. So I often did a 32 run for my screening. But I think you'll do best if you focus on trying to do a 16-run DOE, and that way you have plenty of room for lots of factors, and plenty of room to actually convert this into a characterizing design. Another option, as I'll show you when we do characterization, is to just do 8 here, so you have 7 factors, and then do what's called a fold over to give you that 16. I'll show you how to do that when we get to it. If you want to run a 16, I would just refer you to the previous section because that's what we've covered. Okay, let's do a screening design example. All right, here's an example of a screening design or of a situation where we might do a screen. Here, it's not all that clear. We only have 7, so I might go ahead and run a 16-run experiment, and that would give me a resolution 4 design. I just know that from experience. That's not an obvious thing. Okay. However, suppose we wanted to screen out what was important and what wasn't the first time around. How would we do that? Well, one of the ways would be to say, okay, we have 7 factors, let's screen out what are the important factors and what aren't. One of the ways you could do that would be to run an 8-run design. So a 2 to the 7 minus 4 design. Okay, so let's just take a look at what that would look like. And we might want to start out with that. So let's just take a look at what that would look like in Minitab. Okay. And if we generate that for Minitab, we'll get something that looks like this. I'll go ahead and do that. Yeah, I'll go ahead and do that in Minitab. So here we have 7 factors, A through G. Factorial, create factorial design. 7 factors, display available designs. Well, here's our 8, and it says a resolution 3. Go ahead and choose that. Whoops. And there it is right there. We could note all that. And suppose we went ahead and did that. Well, let's take a look at the alias structure first. Here's our alias structure. You can see that A is confounded with B, D, C, E, F, G. There's a lot of confounding here in the structure. So the likelihood is that we're going to be able to look at only the main effects. Suppose we did that, and we actually put it into action, ran it. We might get, suppose we got this response. Okay, so suppose we actually got that from Minitab, ran the experiment, and got this response. Maybe we're looking at handle time. And so I'm going to analyze that right now. You'll see it gets analyzed exactly the same. Okay, stat DOE factorial, analyze factorial design, same old here. Let's keep them all in there, but boy, there it is, and it's not looking all that great, right? So, and this is one of the problems with this, is that when you do this screening design, you often get things where it's a little bit mixed. You get some things that are important and some things aren't. So now let's start to remove some of the ones that are less important. So let's remove the G and the B factors. Those are at the bottom. We'll keep everything else. Again, you could remove a little bit more and be aggressive, but let's move the B and the G factors. The BGs. Okay, that's all of them, all the main effects, and now we'll just move this guy and the G over. Let's take a look and see what we get. Okay, when we do that, now we can actually get p-values, and it looks like A, C, and E are significant, right? Okay, so any follow-up experiments certainly would have to have A, C, and E. Remember, we're being a little bit aggressive, so I don't mind cutting out D and F on this one. So that might be the way that we would proceed, you know. Now, again, to me, this is a nice way to prioritize things. The idea that we did it with 7 is perhaps not the best screening situation. In any event, we got the results that are given on slide 86 in your book. That's a screening design. Now let's go ahead and let's take a look at characterizing designs. And we'll use the same example. Now, if we did this, if we did a characterizing design and we wanted to go straight to it, we might want to say, well, why don't we just run a 16-run experiment with 7 factors? Where would that get us? So if we take a look in Minitab, see you later, Pareto. And we did a DOE. Let's create one. 7 factors. Maybe we could go to 16 runs or 32. How about just going at 16? That's a resolution 4. Might be good. So I could go ahead and pick that. I might be able to do a pretty darn good design here. And now you can see my aliasing is nowhere near as bad as it was before. I've got A confounded with BCE, so the 1s with the 3s and the 2s with the 2s. Those are fairly easily handled, as we'll see in just a moment. Excuse me just a moment. Oh, the pollen is really crazy here. Okay, so we could run this one instead. Now, an interesting alternative is, suppose that we've already run the screening data. If we've already run the screen, what we can do is a fold-over design. Essentially, what that is you take 2 of those 8 blocks of runs, right? A 2 to the 7 would be 128. So there's lots of blocks of 8 that are in there. And essentially all we would have to do is find another block of 8 that's in there. That's in that 64. To show you what I mean is if we ran, here's 16. If we ran, when we did a DOE, factorial, I'm going to create another one, and I'm going to not randomize this time, and I think you'll see why. So you notice that the standard order is not the same. Standard order is like a standard order that Minitab uses to do the 1s and the 0s, and the 1s and minus 1s. And then it does this run order, which includes randomization. You should include randomization as a general sense, but if you didn't, and let's just do the, let's just do the full. Okay, so here's our full, and well, I feel like I'm full of something for doing that. Okay. So here's our full, and you'll see it goes down to 128. Now, there are basically, and here's the standard run. You see -1, +1, -1, +1, -1, +1. If you went all the way down, you'd see that that's the pattern. -1, -1, -1, +1, +1, -1, -1, +1, etc. Minus, 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 plus, 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 and etc. I'm not going to keep going on that. Okay. If you took a certain block of 8, which is what we have already done, then you could take any other block of 8, or you could take another block of 8, and that block of 8 would make up your full 16 if you did it in a smart way. Well, it turns out that one of the tricks, and this is just a trick, is essentially to what's called a fold over. So you take all the 1s and the -1s, whatever they are, and you essentially fold over the design by changing all the 1s to -1s and all the -1s to +1. So that's what happens if we put it in run order. okay, and we fold over this design. Now remember, we already had our responses for all of that. We already had our responses from the previous call center screen. You see this? 1 through 8. So essentially what I'm doing is I'm taking this, and I'm just changing all the +1s to -1 and all the -1s to +1. That is this right here. I've just repeated it there so that you can tell the difference. So if we've already run this, we simply then run this right here. Okay, and you'll see that that's all the -1s changed to +1, all +1s changed to -1. That's what we do. So that's how we make up the next 8 in the block. Now you might want to say, well, wait a second. If I was running a screening to get rid of the A, B, and C and all those, remember we found B and G were not significant. Why am I including them in here? Well, the reason is because you get them for free anyway. So if you do 16 runs, you know, here's a thought. Sometimes people will say, well, I have like 3 or 4 factors, or I'm sorry, I have 5 factors. I can make 16 runs. I would often encourage people to say at least go to, say, 7 by thinking about what are noise factors that you can control by putting them into the experiment. In any event, we would run this guy right here and get the full response right there. Okay, so this would be the full experiment, but remember, you're running it in 2 segments. This would have been a preceded screening experiment, and then this would be the follow-up fold over, and it gives you a continuous big experiment, or 16 anyway, which does that. Okay, now we've already analyzed these in characterizations, and it works the same way. It is as if you just created this right from the get-go. So we'll go ahead and do that. I'm going to analyze that mini-tab. Do that too much, altogether too often. Just closing down on my worksheets here because I don't need them. There we go. Okay, DOE, analyze factorial design. There's my factors. Low, high. Here's my response. Now we'll see that this is a res 4. I'm going to leave them all in. Graph, there's my Pareto. And now when I analyze the mini-tab, again, I can do the same sort of thing. I get A, E, and AE. So I started out by doing the C. Remember I got A, C, and E were the big hitters when I did the first screen. Now let's see what that really is. Aha! It looks like C is confounded with some things over there, and E is confounded with some things, but the AE interaction confounded with some other things. Well, it turned out that C is not a big deal. You know, sometimes you get spurious things when you run 8. All right, but the screen, again, it did what it needed to do. It did a good job at chopping finding the things that were important and eliminating most of the things that were not. Okay, we know the next steps would be to simply take this and eliminate all the terms except for the main effects and the AE interaction, and then we get that. Okay, let's go over a couple of examples of this, and these are located in the okay, so just a couple of the exercises that you'll get in the homework. The first one is exercise 1. This is just for a discussion about how you would think about controlling noise, how you decide it. This does happen to be an experiment that is an industrial experiment done at a shop that makes amplifiers. Having said that, I wanted to choose something that was perhaps a little bit outside of your comfort zone, so you can talk about what the response is, what the factors are, what the levels are, what are the noise factors, and then think about how, even though you don't know anything about this particular, or you may not know anything about this particular industry, you can still recommend a reasonable experiment to this person. All right, let's go through on this example as well. So in this one, we're talking about screening designs, and we have probably another one that you're not familiar with. I'm certainly not familiar with, truck springs. But in this case, the goal is to design, suppose we conducted an experiment to improve the heat treatment process for truck springs, and the goal is to produce springs that have a standing height of 8 inches. Now the engineers chose 5 factors. What would be a screening design to start out in this? Okay, so one way to do this would be to just go directly to Minitab, and let's see what we get. Okay, so we have 5 factors, an appropriate screening design, and you can probably guess this. But if we have 5 factors, a screening design might be a quarter fraction or 8 runs. Okay, so here, right here again. So we might be able to do a screening design in 8 runs, and there we go. There's our resolution 3 design right there. Okay, and I'd like you to do an analogous example from your own industry or everyday life. Now let's do actually a real experiment that was done on this one, maybe in a follow-up. This would be more of a characterization experiment on truck springs to analyze the data for the response F bar. Now notice that they essentially did 3 repeated measurements, and then they averaged that. That was their experiment. So we take care of the what is resolution, which factors are significant, write your own f of x model. These data are given in, not in here, but in the truck springs example right here. Let's pop that into Minitab. Now, what's interesting in here is we often talk about this for another course, but DOE can be used to optimize any sort of response. This one, for example, could be used to optimize. You can imagine with springs are vibrating around, not only do you want the average height to be the same, maybe you want the standard deviation to be the same. And so for this one, we use something called loss function, and we try and minimize the log of the standard deviation squared. I won't go into that theory, but I just want to point out that you can use different responses than just the average or just the signal. You can minimize variation. DOE is great for that. Okay, so in this case we want to do F bar. Let's just go ahead and analyze that. Five factors, low, high. Here's my F bar. I'll keep them all. Graphs, Pareto, 0.1. And there I go. So I get a couple of interactions. I get A, E, B, and B, E. So I go ahead and analyze the rest of that. Now it's interesting, it's asking for the resolution of the design. You should be able to go up to the session window and see, for example, what the resolution of the design is. Ooh, that's not that one. I didn't think it was. Let's see, we've got 16 runs, 5 factors, right? Should be res 5. No, I'm not seeing it in here. Okay, so here it is right here. And we're analyzing it. Well, I was wrong. It's a res 4. So here it is right here. Let me just make sure that that's right. I'm going to give you any wrong answers here. 5 factors. No, it should be a res 5. 16 runs. My truck springs data. Something's not right. Let me try this whole thing again. Something isn't right. Start a clean Minitab so I can see it all. Minitab session window is such that it logs everything in there, and it sometimes makes it difficult to really see things. So I often like to clean it out. Okay. Factors are A through E. Maybe I accidentally selected an extra factor or something. There's my response. And let me just look at that graph. Here we go. So this time I really should get it. There's my graph. Yeah. Okay, yeah. So here's my here's my confounding, and yeah, it is a res 4 design. So I've got my 1s confounded with some other 3s, and I've got my 2s confounded with other 2s in the worst case scenario. So we go back and we'd analyze the rest of this. Should be a res 5. I don't get it. Something was not right about this design in here. So that's interesting that we're noticing that, right? Because it should be a res 5. Minitab was saying that. Let's go ahead and eliminate some of the non-important terms. Take a look at the graph. BE interaction. Everything but BE. And there you have it. And we probably get rid of C at this point too. So at this point we can get rid of C. We'll have A, E, B, B, E, and D. And that would be our model. Okay, let's look at one more thing here. And what I want to do is I want to show you maybe one thing that you could do to look for, sort of finding where is the best place. But we're going to cover that in just a moment. Really in optimization. I do want to show you, basically, you'll get a homework assignment based on this. So I'm going to show you something called the DOE Machine. And it's a little bit different, but in the DOE Machine, which is the exercise that's on 106, which you'll get in your homework as well, it says on each sheet you'll find a model that simulates real-life situation. Your job is to use some sort of strategy to efficiently determine the best operating points for factors given. So the idea is not only to find what factors are significant, but to find the actual thing that gives you the best response. Okay? And predict what response will be given given your settings. You might want to use a screen first and then a characterize method, okay? Drawing the box and thinking of an example. Okay, so I'm asking you to say, start out from using an example using 7 factors, and then in Model 1 we're trying to minimize the response. For example, in this case, maybe cycle time would be a nice analog for you because you've got 7 factors trying to minimize the response. Cycle time you want to be low. Okay, so let me show you what we're talking about here, okay, so that you can see it maybe a little bit more clearly. Oops. So let me open up DOE Machine, not Bicycle. I've been threatening to do Bicycle for a long time. So let's do this one, which the first one, which is to minimize. And it looks like we've got 5 factors. That one's pretty simple. So let's do that one. I like simple. Okay, so one of the things we might start out by doing is to say, well, let's go into Minitab and have Minitab generate for us a design. I should do what you guys were thinking of, and that is to say, draw the box, and then say, here my output is, I don't know, cycle time, And what are my inputs? Well, I don't know. My inputs are amount of gas in the car. Maybe I'm thinking how far the errand is. Maybe I'm thinking of driving someplace to the doctors or something like that. Okay, etc. All right, so you should think of your own example. We'll just go ahead and do this in Minitab. So 5 factors. I want to run an experiment to figure out, to crack the code as to what is the formula for this. So let me see. Maybe one way to do it would be to run a factorial design. I don't know. So I have 5 factors, and I want to do it fairly efficiently, and I want to spend a lot of money. So I think I'm going to do 16 runs. I could do a screening experiment in 3 and then fold it over into 16. I could do that, but instead let me just do 16 runs. Okay? So I'm going to go ahead and do that. I could maybe save a little money by doing that other. And so here's the experiment that Minitab told me said is the right combination of factors. I'm going to port that over, paste it in. And now what I'm going to do is I'm going to start to copy. Let me do this one first. So this is 1, 2, 3, all the way to 16. And watch what I'm going to do. I'm going to actually run these sequentially. So the first one would be this. And I'm going to paste this as a transpose. There it is. So it should be 1, minus 1, minus 1, minus 1, minus 1. There it is. Now I hit run the experiment. Watch what happens. Bam. This will be experiment number 1. Okay. So with those factor combination, it gave me that response. Okay. Let me continue. I'll copy, paste the transpose. Okay. Double check. 1, minus 1, minus 1, plus 1, plus 1. Run experiment. This will be experiment number 2. Okay? See what's going on here? And yes, it is a little bit tedious. One of the reasons why I wanted you to do this is because I want you to get in the habit of being able to say, oh, it's these settings. Get it. Okay. And I'm just going to mark these as complete. All right. And if you keep doing that, you will get something that looks like this. For example, if you run 16, you might be able to get away with it in doing 8. And then you can copy this and put it into Minitab and analyze that design. And I'll just show you what I got in this case. Here are my factors, my low and high, my response, do my graph. I'm going to do the normal this time. Aha! I've got A, BE, AB, BC, and C. A lot of interactions there. A lot of interactions. So I got to write those down. Let's see. BE, AB, BC. Okay. Take out the others. A, B, C, D, E. What was the others? A, B, B, BE, BC, and BE. There they go. Okay. So now this is my model. Looks like it is those. So I've got to have A, B, C. don't need D. I need all the others. There it is. So then this would be my model. Would stop at this. Notice I do have a B term in there. I know if you, I've been looking at the Pareto so much, I want to see it now too. There's my Pareto. Okay, got it. All right. But okay. And so now I can write down my model from this, right? Here's my constant. Here's my A, B, C, E, A, B, B, C, and B, E. And now I want to figure that out. I want to see which one gives me the minimum, right? Because I want to minimize my Y. So I want to plug in these values for A, B, C, and E such that I get a minimum value of Y. Okay? I'll let you see if you can struggle with that one a little bit, but that's how it works. That's how it works. The DOE machine, you've got 2 of them, and go to it. Now it says you can set them between any number between -2 and +2. That's for a different class. That really is for optimizing, for finding super duper sweet spots beyond the normal stuff. That's optional for this class. Okay. All right. Well, anyway, I hope that you found this illuminating and helpful, and we'll see you a little bit later.